Welcome back. Welcome to How to Teach Science and Engineering Part 3. In this lesson, we will start with how not to teach. I'll give you a typical example how science is being taught. What's wrong with it? Examples of bad teaching. After that, I'll show you how to teach well. Good teaching. Often the teachers go to the class, write a topic, let's say electric potential. Then they define it. The electrical potential at a point P is the work done while bringing a unit positive charge from infinity to that point. They just copy it from the book. Not very good books. Some textbooks are not very good, we know that. They write this definition, read it, then they write some formulas. A typical formula for this would be like that. Then they derive some more complex formulas. Just copy from the book, line by line, and read it. It's got many symbols. They don't tell the meanings of the symbols, but they continue, derive some other formula. Students, right in the beginning, think like this. This is a real example. Many students have asked me, why would somebody go to infinity, find a unit positive charge, and bring it to that point, P, just to find out what the potential of that point is? This is a real question. Several students have asked similar questions along the same line. It doesn't make sense to them. You have studied a lot. You know where it will be applied, why it's going to be useful, but you start with a very difficult definition, and this is realistic. Can you go to infinity? Can you find a positive unit charge? Can you bring it to a point? Then what's the point? So you should change. Okay? So, very intelligent students ask this kind of questions. Doesn't it have a simpler meaning? Why don't you use that one first? All right, let's see. That's a typical example of a bad teaching method. It seems like copying from a poorly written textbook, writing it down and reading it. Why the students can't do that? They can read the books too. Why are you teaching them? Okay, it does not tell, these are the problems. It does not tell why learn about electric potential. What is the use of this concept, electric potential? It does not give any real-life example. Realistic numerical values, lots of formulas, complicated formulas. No visualization. How does the potential change? No animation, no plots, no analogies, how this electric potential is similar to the other potential energy that we need, that we have read, they have studied, you have taught. They do not grasp the concept. They get lost right in the beginning, the second sentence, at the concept, and do not follow the rest of the lecture. Whatever you teach after that is useless, doesn't go into their head. So they have not understood the first line. They end up memorizing from the book, complaining about how the teacher is not good, how they don't understand, how physics is bad, how physics is difficult. They memorize, note down whatever you write on the board, they write it down in their notebook, and they hope to pass the exam. Failure of learning. Their fundamentals remain weak. They quickly forget what was taught and cannot use this concept or any of these concepts to solve real problems or invent something new using these concepts. Okay? They pass somehow by struggling. This is a bad way of teaching, but this is what many of us do, unfortunately. Now let's see sample of good teaching. Okay, are you ready? All right. How to teach science and engineering subject, part 3. How to become a rocket scientist. That's what we are going to learn today in the class. Okay? Students get excited. Today, we will see how learning physics will help you become a rocket scientist. You learn how airplanes fly and how rockets work. By the time you finish this class, you'll be a step closer to becoming a rocket scientist. Rocket scientist is an informal name for aerospace engineers. Of course, if you pay attention, you have to pay attention to what I'm teaching today. If you participate in this class, do the calculations I asked you to do, then in the end, I'll show you a great movie. Okay? All right, let's start. Newton's laws of motion, you have learned about first law and second law. If you have any questions, you can ask me later. But right now, we are going to learn about Newton's third law of motion. Okay? What do you feel when someone pushes your hand? Pushes your hand. Do you feel some force in your hand? Okay, you do? Good. Somebody pushes your hand. Good. Suppose you push a table. You push a table or a car or onto the wall with your hand. Do you feel anything in the hand? Try it. Try now. You're pushing the table. You feel the same kind of force as if somebody else is pushing you. So what is happening here? Suppose somebody pulls your hand. Do you feel? Do you feel that your hand is being pulled? Now you pull the table or try to pull a car. Do you feel the same kind of force? As if somebody is pulling you? Most of the students would say yes. Yes, let them try right away. What can you conclude from that? Think like a scientist. Let them answer. So when I push, it feels like it's pushing me back. When I pull, it feels like it's pulling me back. So this is what Newton also thought. And he wrote down, for every action, there is an equal reaction, but in the opposite direction. That's Newton's third law of motion. What that means is if you push something, it pushes you back. If you pull something, it pulls you back. If you apply a force, there's an equal and opposite force applied on you. If you apply a force on a body, the body applies a force back on you. Okay? Here, the term action and reaction, they mean force. Okay? This is a force, this is a reaction force. Okay? The action and reaction, these words can be used in different contexts to mean different things. For example, in chemistry, a reaction has a different meaning. Okay? Here, it simply means force. Let's understand this. A body applies a force on another body. The second body, let's say this body applies a force on this body. How? Maybe there's a rod connecting. This one pushes somehow. This body pushes it back. This body back. The same force, but in the opposite direction. If this one is a cable or rope, This one pulls, so this body is being pulled. This body will pull with this rope on this body. Pull back. Think about this. Try it. Try pushing the table. Looks like it's pushing your hand back, right? Okay, so this is very important law. You have to think about it for a long time. So suppose I take a piece of wood, my favorite experiment. I take a piece of wood, just leave it there. What happens? It falls down, right? It falls down. If I put that on a table, it doesn't fall back. It doesn't fall down. What is this body doing to the table? Try putting a book on the table. What do you think that body is doing on the table? It's actually pushing the table down. If the table wasn't there, it would fall, but now it's not falling. It's pushing the table. What do you think the table is doing to the body? This is what is happening. The body is pushing the table down because it's got weight. It's got weight. That weight is a force. Okay? Weight is a force that always acts downwards on a body or object. Okay? You'll learn more details later in another chapter about weight and why it's a force. But for now, just assume that weight is a force. It's got a direction, magnitude. The heavier the body, larger is the force, direction always downwards. So if you are here, say in the northern hemisphere, it goes down that way. If you're in Australia, which is, suppose that's the Earth, Australia, it goes that way, but always towards the center of the Earth, okay, downwards. So the body is pushing the table down. What would the table do? It will apply equal and opposite force on the body, upwards, okay? As soon as you lift it up, there's no contact. The table doesn't feel any force from there, from the body, downwards. The table also doesn't apply any reaction force upwards. So if you take just the body, I've separated that just to show these letters, the words, okay? When they are in contact, this body is pushing on the table, and table is pushing back with equal and opposite force on the body. So on the body, what force is acting? One is this weight. Weight is acting down. Now there is the reaction of the table, opposite direction. They are equal and opposite. So they cancel out. So the body does not move. Newton's first law of motion. Total net force on this body becomes zero. Weight is pulling it down. Table's reaction force is pushing it up. They cancel out. They're equal and opposite. It's not very easy. You have to think about it. Okay? So anytime there's a force applied on a body, the body applies equal and opposite force on the body that was applying the force. In this case, it's you. If you are applying a force on the body will apply equal force back at you. Okay, so I'll assign some homework right now. Take a picture of this. Read through it. It's very simple. This 1 kilogram brick falls down from 44.1 meter tall building. It takes 3 seconds to fall down. Fall 44.1 meters in 3 seconds. It hits the ground. What is the force acting on it? Think about it. It was at zero velocity here. Velocity increased, and you know, only external force can make a body move. If it's moved, there was a force acting on it. That's what That's what moved it. So from this data, you got to find out, and force causes acceleration, Newton's second law of motion. You got to find out what was the force on the body. Okay? And then check that force, and this multiplied by this 3 seconds, is that equal to change in momentum or not? You know, force is equal to mass times acceleration, which is also rate of change of momentum. How much momentum changes in 1 second? In 3 seconds, how much? So find out if this is true or not. Okay? The second one, a father and a child go ice skating. If you don't know what ice skating is, look up the internet. So it's on a special kind of shoes. On plain ice, you can move. Okay? Very interesting. How do you move on ice? It's very difficult to understand. Okay? But let's say they go there. The father weighs, it's not weight, it's actually mass of 80 kilograms. But we say he weighs so much. She weighs so much. He weighs so much. I weigh 70 kilograms. So the father weighs, that means he has a mass of 80 kilograms, and the child 10 kilograms. They stand on the ice, and then the father gently pushes the child forward so that the child can start moving with a 10 Newton force for just 1 second, and then releases her. She keeps moving. What is the momentum of the child? You need to find out. It's all from second law. What is the momentum of the father? And what's the total momentum? You know that momentum is a vector. Mass times velocity. Velocity is a vector. So momentum is a vector. So remember to take care of signs, plus, minus. Okay, ignore the resistance friction of the ice. You may not know what friction is. But let's say ice is so smooth that you can ignore any force coming from the ground to the child. So all other forces ignored. Father applies a force on the child. So you have to use Newton's third law of motion, second law of motion, and the kinematics that you have learned earlier in some other chapters, other lessons. Is there anything interesting you can say about the result? You have to look at the result. Momentum of the child, momentum of the father, and total momentum. Can you say something about the result? Can you come up with any hypothesis? Okay. Imagine that you're a scientist. Like you look at something, you observe something, you calculate something, and then, oh, this sounds like a law. So you create a hypothesis. Once it's tested many times and proven to be true, it becomes a law. Okay, try to come up with one. Now, from your textbook, at the end of the chapter, there are many problems given. Choose a difficult and interesting problem that you think, yeah, it's important, and try to solve it. These are 3 homeworks. There are some hints given here. Always draw some kind of sketch first and write down what's given, what's not given. What do they want? Finally, what answer you're looking for. Write them down, okay? Write down all the known values. Think about what is asked, what we are trying to achieve, what is given, how would you approach the problem? Okay, it's a dynamics problem. I know Newton's laws of motion. The second law of motion will tell me about the relation between the force. I know force, yes, very good. It talks about acceleration and mass, yeah, so I can get acceleration. Think like that. From that, I can tell what the final velocity is using kinematics. I know if I know the acceleration, you know the initial velocity and acceleration. Initial velocity is 0. Acceleration is, I can get the final velocity if I know time. Okay? Or distance. Okay. Think like that. Approach. What approach will give you the answer? How would you reach the goal? That's our goal, to get the answer. What principles, laws, and relations, Newton's laws or something else, kinematics, what do you need to use in this problem? What assumptions you are making? For example, here I wrote that ignore the friction of the ice. If this was not given, still you have to make that assumptions, write down, I'll ignore all other forces, frictional force, etc. Okay? Simplifications, write that down in one line. Think about the steps. First I'll do this, then I'll do this. From there I can get that. Think about the steps. Then you solve the problem. Formulas have to be correct. If you use wrong formulas, you'll get wrong result. Of course, numbers have to be correct. Here it says 44.1. By mistake, you cannot write 41.4. Okay, numbers have to be correct. Units have to be correct. Suppose I mixed up the units. Here I give meter, and here instead of Newton, I give some other units. Or here I give, instead of kilogram, I give gram. You have to convert into kilogram. Okay, consistent units. Calculation, using the calculator or in your mind by hand calculation. Whatever you do it correctly. Many times mistakes happen in calculation. Final solution, final results, you have to highlight. Mark it very nicely in a rectangular box maybe, so that those who are checking your calculation can very quickly say, yeah, this is the final answer and this is correct. Check the result. After you get the results, is it making sense? Suppose here you get something like momentum is 20 million. Well, of course, it's wrong. Okay, you got to have some kind of sense. All right. Check if the result seems reasonable. Sometimes too little or too much information is given in the problem. Okay, some things may be missing. You have to make some reasonable assumption. You cannot say, I cannot solve this problem. Make reasonable assumptions. Suppose the force was not given. Take F. You get some kind of formula at the end. Or you can say, let me assume it's 20 newtons, which is reasonable. But do not take 2000 newton. You know, a father will not push a child with 2000 newton force. He himself cannot apply that much force, okay? Choose something reasonable. Many things are not known, but still we create things that work. How? We make reasonable assumptions. Okay, sometimes too much information is given. If you try to include everything, air resistance, somebody is blowing, okay, there's a piece of rock on the ice, all that if you want to include, you cannot solve the problem. Okay, it gets too complicated. So ignore important, unimportant information. Ignore, okay, there may be too much. Make a habit of doing systematic, neat work. Do not say answer is correct, but nobody can read it. Systematically write down. Why am I writing everything so systematically? I could come and give some kind of lecture and make a mess here. I spent hundreds of hours creating these simple things, okay? Systematically. Still I can improve on it. Make a habit of doing that systematic, neat work. It helps the reader. Also, it helps you. When you want to look back, you know what you have done if you work very neatly, clearly. Okay, let's go back to Newton's third law of motion. When a body exerts a force on a second body, one body, anything, any piece of matter, mass, exerts a force on a second body, the second body simultaneously, in British English is called simultaneously, American English, simultaneously exerts a force equal in magnitude and opposite in direction on the first body. Okay. You have to memorize this, because if somebody suddenly asks you, you say, oh, I know what it is, let me explain. You cannot take 10 minutes to explain, or in your exam or interview. Okay, so you have to memorize this, but you have to know everything that's written here. You have to understand it. That's Newton's third law of motion. How he came up with this is amazing. You did a simple experiment, pushing the table and fill, trying to feel. Okay, example, explanation, calculation, application in the problem solving, force on our heel. Unless you give realistic examples, students will not understand. Okay, this is how it is. Immediately give realistic example. In fact, you can start with an example. And then concepts will come, definitions will come. Okay? Textbooks are different. Textbooks usually define something, then explain. You could do that, but it's much better to teach by teaching the concept and understanding first, then define it. Explain it just the way I was explaining. Show some calculation. Application and problem solving. Newton's third law of motion applies anywhere. Anything that's being pushed, pulled, Newton's third law of motion applies. Okay? So, now you know that when the book is on the table, or a block of wood is on the table, is pushing the table down. Similarly, when we stand, our body's weight is pushing us down on the ground, and the ground pushes us back on our feet, on our heel. When we walk, how much is the force on the heel? Think about that. Weight is a force, don't forget. Our body is trying to come down. On the heel and on the foot, entire foot, the ground is pushing back so that we don't fall down. We stay on the ground. Okay, equal and opposite force. Let's say the entire weight is supported on our heel. How much is the force on the heel? You have to find out. When we walk, sometimes there's just one heel touching. Okay, or when we run, entire force, it goes up when we are running. Okay, now here's a realistic example. If a train engine, let's say this is the train engine, is pulling the cars are connected with some kind of links. Okay, you have some kind of links. They are connected, and the engine is pulling this one. The cars are pulling this engine with the same force in the opposite direction. The engine is pulling the cars are pulling with the same force in the opposite direction. And why does the train move? Very confusing, right? Okay. On the engine, there's some external force that's coming, being applied from the tracks, from the rail tracks on the wheels, just the way cars move. Okay, that force is much larger than this force on the engine pulling back. That's my cat. Okay, she wants to learn physics too. Okay, so that's a different force. You cannot misinterpret Newton's laws of motion. Newton's laws of motion. If you apply in the wrong way, just playing with English words, it can get very confusing. You have to write down what is happening on one car. Let's say this car. This car is pulling it with some force, let's say F2. This car is pulling it back with F3. As long as F2 is larger than F3, this car will move in this direction. The net force is in this direction. Okay, that's exactly what's happening on the engine. Engine is being pulled back fine in this direction by F1. But the ground force from the ground, the rail tracks on the wheel is larger than this F1. So the engine wouldn't move. Okay? Think about this. It's not that simple. Okay, good. Explain the forces in the engine and the cars. I just did. Now think about this. Newton says, Newton's first law, a body It will keep moving in a straight line with constant speed, uniform speed, unless external forces apply. But the planets, they are in space. They are free to go in straight line or constant speed. Why are they going round and round the sun? Let's say if the sun is here, Earth is going round and round. You know that, right? If you don't know, study in geography. Okay. Why is it going round and round, not in a straight line, uniform speed? Think about it. We'll learn about these things later. I'm just making you think. Using all three laws of motion and problem solving, all these laws are related in some ways, okay? Newton's laws of motion. Most of the time, all three laws are applied together, okay? They're all related. Now comes, how does an airplane fly? I'll give you a very simple explanation. And here you'll see how all three laws of motion are implemented. Suppose there's an airplane, okay? Staying on the ground. Stationary, it's not moving because there's no external force on it. Yes, there is an external force. On the wheels, there would be some reaction force from the ground, which is equal to the weight of the airplane, so it's not moving. Total force is zero. The pilot turns on the engine. Let's say the engine could be here under the wing. This is the body of the plane. This is the tail plane. Okay. Here's the pilot. And there's the wing I'm seeing from the side. Okay. The engine could be under the wing, here, there. Let's see. It turns on the engine. Let's say it's a jet engine. Okay. Jet engine pushes hot air through the back, okay, from behind the engine at a high speed, pushes the air back. The air's momentum is changing. So what that means is there's a force on that hot air, okay? Rate of change of momentum is equal to force. So what would that hot air do? Newton's third law comes now. It will give a reaction force in this direction on the engine. Hot air is being pushed that way. Hot air will push the engine that way. Engine is connected to the airplane. Airplane will experience a horizontal force in this direction. So airplane will start rolling, right? It will start moving if there's enough force. You got to turn on the engine quite a bit, all the way, okay? Then he releases the brakes, the plane starts moving forward. The plane moves forward, the air flows on the wing. The wing shape is such, it's not a flat plate like this. Wing has a very nice shape, a little bit like this, okay? I'm seeing from the side, okay? These are designed very precisely after many years of work. Engineers have come up with shapes. This shape is such that airflow goes down a little bit. In fact, the pilot makes it curved like that, okay, by pressing some switches. Makes it curved like that. So air is flowing. Plane is actually moving into the air, but we can say similar to air flowing over the wing, okay? As if air is flowing from. If you run into the air, do you feel that air is blowing against you? It's the same kind of thing. Air flows over the wing. The shape of the wing is such that the air does not flow straight, it curves down. So what are you doing? You're pushing the air down. If you push the air down, making it flow down that way, you're changing its direction. Change of direction is also acceleration. Okay? So there is a force on the air that's pushing it down. The reaction force is on the wing upwards. The faster you go, the higher is the force. When this force, that's called lift force, becomes more than the weight of the plane, so there's a net upward force that lifts up the airplane. The airplane goes like that. Slowly the lift force is increasing. Weight is constant. Lift force is increasing. When lift is slightly higher than the weight, the plane takes off. Okay? When you learn more about flow of air, etc., then you'll find better explanations. But this is absolutely correct, what I just said. The plane's wing shape is such that it pushes the air down, doesn't let it flow straight, it pushes down. So the air pushes the wings up. Once the wing is being pushed up, slowly the plane starts moving up. That's how it flies. Okay? Got it? Newton's laws of motion. Later you'll learn more details how the pressure on top is slightly lower than the pressure. You probably have not learned what pressure is, but we will explain those things later. For now, you know it's because of Newton's laws of motion. We saw second law, first law, second law, and third law. All three act, making an airplane fly. Good. So where are Newton's laws of motion applied? Second and third law of motion. So this is actually a simulation of diesel engine, car's diesel engine, or maybe diesel engine that's used for ships or pumping water, whatever. Diesel engine. These are called cylinders. Okay, they go up and down. Here's the hot diesel and air mixture burning. They push this down, and these are called connecting rod, and this is called crankshaft. It just goes round and round like this, and that drives the motor, the car. Okay? A lot of things are moving. Newton's laws of motion. To find how much force is acting on these parts, you have to use Newton's laws of motion. Okay? Many parts, such as piston, this is called piston, that's connecting rod, that's crankshaft. All these things are in motion. As soon as any body is in motion, Newton's laws apply. You have to find those forces using Newton's laws of motion. Once you know the force, then you can design these parts so that they're strong enough. If you don't know that, it will be very difficult to design. Okay? Once we know all the forces, we can design the parts to be strong enough. Otherwise, they may break or may be too heavy. Without Newton's laws of motion, it will be very difficult to analyze and design machines, any machines. Even things that don't move. See a bridge, doesn't move. Suppose that's a bridge, here's a support, here's a support. It's not moving. That means Newton's first law of motion apply. All the external forces put together is zero. The weight and the support reactions, all of them are all put together as zero. With those forces, you can calculate how strong you have to make the bridge. Okay? Newton's laws of motion apply even when things are not moving. Good. Now, application. Well, that looks like a rocket. I wanted to make you a rocket scientist. Let's see, the first step. Here's a question. A rocket at the launch pad, let's say that's called launch pad, it stays there, it's not launched yet, has a mass of that much. Wow, that's a lot. That's 1 million, 10 to the power 6 million kilogram, 2.97 10 to the power 6, 2.97 million kilograms. Okay. Thrust is a force that the rocket engine produces. That means the rocket engine pushes the burnt fuel down, and reaction, that one is called thrust. Okay, thrust. That's a force. The 35 million, again, million, Newton. It's a Newton. Thrust, upward. Okay. What is its acceleration at liftoff? For planes, we say takeoff. For rockets, we say lift off. Okay, that means start. Okay, so first thing to do is draw a simple diagram. Very simple. Don't make it too fancy. Don't write too much details. And then draw these simple forces. So there is a thrust. That much thrust is given. And that's my simple rocket model. I'll simplify. There's a weight of the rocket too. It's got a mass. Okay, it's got a mass. We would say the entire body's mass is acting somewhere at the center. That's what we'll assume. Okay, simplification. And there's a thrust acting at the back of the rocket. Good. Approach. Newton's laws of motion. We have to use it because it's about to move. It's got force. It's got acceleration. Newton's laws of motion. Second law. Okay. Weight. How much is the weight? You probably don't know this formula, but this is what we do. We multiply mass in kilogram by 9.8 to convert that into Newton. Okay. You don't know that yet. Maybe if you did the homework, maybe you figured it out. Even if you didn't, it's okay. Just assume for now, if I multiply mass by 9.8 or 9.81, it converts into Newton force, the weight. That gives me weight. Okay? Net force. Thrust is acting that way. Weight is acting this way. So net force will be thrust minus weight upwards. Thrust, let's say upward is positive. So I'll put that one as positive and subtract the weight from there. And this is what I get. Thrust I get from here. 35 minus that much. That gives me that much. 5.894 million Newton. That's the net force acting on the rocket upwards. Okay? So acceleration, how would you get it? Newton's second law of motion relates force and acceleration. Now you have net force. Acceleration you can get from Newton's second law of motion. F equals ma. A is the acceleration. M is the mass. So I can get A by dividing both sides by m. F divided by m is acceleration. I plug in the values. The force is that much, net force upwards, divided by the mass, and I get 1.985 meter per second squared. Acceleration is important to write the unit correctly, okay? So about 2 meters per second squared. That's the acceleration. Very slow. Very slow. When it lifts off, very slowly, okay? But you have to verify the data from internet, find out the data if these things are reasonable data for a large rocket, and then discuss with fellow students if these things make sense. Is it too slow? If it goes 0 or negative, that means the rocket is not going to lift off, okay? Has to be positive upwards. If it is very close to 0, it may just float around but not go up and then fall. Okay? Discuss with the fellow students if these things make sense, these data. Arbitrary data can be dangerous. Okay? Use realistic data. What happens to the acceleration as the mass reduces? Mass reduces? Yeah. The fuel is burning and coming out. Fuel and oxidizer. Rockets have fuel and oxidizer both, okay? You learn about those things. Let's say a rocket has got some kind of liquid or powder and some oxidizer. They burn together and come out, and that produces this momentum, change in momentum. So that produces a force, a reaction force, and that lifts off the rocket, okay? Mass is reducing. Force is about the same. Let's say about the same, this thrust. What will happen to the acceleration? Mass goes down, force is the same, acceleration goes up. So it goes faster and faster and faster. Acceleration goes up because the rocket is becoming lighter. Its weight is reducing. Okay? How fast can a rocket go? Well, some rockets can go about, say, 25,000 kilometers per hour. Up, very high up. 30,000 kilometers per hour. Very fast. The beginning starts with 0, slowly accelerates. Acceleration goes up, 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 up. And then it turns, goes around the Earth. It can even go outside the Earth. Okay, so that's the first step of becoming a rocket scientist. Newton's laws of motion, coming back to that, depending on the level of the course, you may, oh, I did not show you the film. Let's see the film.
9, ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
Here we got a roll program. Neil Armstrong reporting the roll and pitch program, which puts Apollo 11 on a proper heading. Plus 30 seconds. Roll complete and pitch program.
Okay. Good. So you saw the movie. You can watch it many times if you want. Okay, depending on the level of the course, if it's school level, college level, high school level, you may want to mention the following points about whatever you teach. Right now, we'll talk about Newton's laws of motion. Newton's laws of motion form a part of classical mechanics. Classical mechanics is the slightly old mechanics, okay? But most of it's almost true. We still use it, most of it. Newton was one of the originators of classical mechanics. It's also called Newtonian mechanics, after his name, or classical. Classical means slightly older, traditional. Okay. Newton's laws of motion can be extended to include rotary motion. We are talking about straight line motions till now. Rotary motion also. We have to modify it a little bit. For inertial or accelerating reference frames, also Newton's laws of motions don't apply directly. You have to modify that. You have to find out what inertial and acceleration, depending on the level of the course. Okay? Reformulation. Newton's laws of motions are very good, very powerful, but sometimes it gets too complicated to solve some problems directly using Newton's laws of motion. Some other scientists and mathematicians, they reformulated. Nothing new was added, only the formulation was slightly different. Lagrangian mechanics, Lagrange did that. Hamilton came up with Hamiltonian mechanics, and those things really help solving some complex problems, okay? So Newton's mechanics is not the only one. There are reformulation, Lagrangian, and Hamiltonian that you learn later. Newton's laws of motion do not hold true at very high velocities. Newton's laws of motion for classical mechanics, somehow we found out, the scientists found out that at a very high speed, things are moving at very high speed, say close to the speed of light, several million kilometers an hour, kilometers per second. Okay? Then, let's say, how much is it? 300,000 kilometers per second, speed of light. So even at 100,000 kilometers per second, Newton's laws of motion start to give wrong results. Okay? There you need to use Einstein's theory of relativity. That's a relatively new theory, 100-year-old theory, and that gives very correct results. Okay? Very small particles, subatomic particle, electrons, protons, you learn about those things later. There also Newton's mechanics doesn't work. Newtonian mechanics doesn't work. Somehow Newton's formulas give completely wrong result. For that, there's completely different kind of mechanics, laws, and mathematics called quantum mechanics. Okay? You learn those things much later. So there's Newtonian mechanics, which you learn. There's at a higher level, you learn relativistic mechanics, Einstein's theory, and quantum mechanics, very small particles. Okay. Further reading, give some good reference. For example, Feynman's lecture. You can ask them to check that one. They can watch Professor Walter Levin's videos. They can read some books, not only what's written in their textbook. Give some homework and get some project ideas. Can you make a tiny little rocket? Warn them about the dangers too. Okay. Please turn in your assignment. Now your assignment is sample video that you have prepared, how you would present, give a lecture to the class. Sample video and turn that in. Okay, to do. Let's build a world where every child has the opportunity to gain knowledge and has the freedom to explore, think, and create. Do not make slaves out of them. Let them explore, let them think, understand, and create. Okay. Start today. Change your way of teaching. Thank you. If you have any questions, I'll take a few and try to answer them. Thank you.